So as is the case with 2D vectors as representations of two-dimensional coordinates, we can do exactly the same thing in 3 dimensions, and we can use a 3D vector to represent a 3D coordinate position. And the notation we use is a continuation and an extension of what you've met already. So you've met the I notation here and the J notation as representing the X and Y directions. Okay, so they're analogous to X and Y in that order. So essentially you would have X going like this, okay, Y going like this, as we did earlier in the 3D case. And now we introduce this third dimension, which is K, okay, I, J, K in alphabetical order. So we have this third dimension, which points vertically upwards, and this is the K direction. All right, now these are vectors. In fact, let me be consistent with this. We're talking about the Z direction, aren't we? Okay, so that's the K direction, which points vertically upwards, which is analogous to Z. So any vector in 3 dimensions can be written in one of 2 ways. So far, we've got the IJK notation, which you can see here, and you've also got the column vector notation. Both mean exactly the same thing. There's no difference. It's just simply a different representation. And you can see just above, we've got I, J, and K as unit vectors. Remember, the magnitudes are all 1. If you applied Pythagoras' theorem to each of these, you would simply get a magnitude of 1. So they're unit vectors. And they also can be written as column vectors as shown. So I think that's fairly simple, essentially. So if you just want to sort of see what that looks like, you've got your I direction there. Now, because it's a unit vector, you could also change that I into an I hat to represent a unit vector. You've got J in that direction, or J hat, completely up to you whether you use the hat or not, and then K in that direction. All 1 unit in length. Okay, so that's how we build a position in 3D space. So let's have a look at some examples where we're actually working with vectors in 3 dimensions, and it's simply just an extension of what you've done previously. So firstly, we've got the points A and B specified as points in 3D space, here and here. And because these are coordinates are always described relative to a fixed origin, O, okay? Now, that makes part A very simple because it asks us to find the position vectors of A and B. So very simply, we can say, well, the position vector of A would simply be, this is for part A, of course, the vector OA. And the vector OA would be, now, I know it doesn't say to do this, but I'm going to put this in column vector form. We have to move 1 in the I direction, 5 in the J direction, and -2 in the K direction. Okay, that would be simply just reinterpreting the coordinates, okay, and writing them vertically as a column vector. So it would take you from the origin to the point A. In IJK notation, it's simply going to be 1I plus 5J subtract 2K. It's as simple as that, really. And we do the same thing for B. So the vector OB, if you didn't know that, just pause the video and try it yourself. But 0, -3, and 7, which we interpret as no i's this time. So we just leave that out. -3j plus 7k. Okay, and that would describe the vector OB. OB being the position vector of the point B. Now, for part B of this question, we have to find the vector AB as a column vector. Well, just so we're absolutely clear about what's going on, if we define a vector OA as a position vector. Now, again, I'm just going to make this up. It's not, doesn't really matter what the numbers are. If I start from an origin and go to A, and just draw it like that. So if that's my origin there, this is my point A up here, then that arrow represents the vector OA. Simply what it means. Okay, so this is the vector OA, like that. Okay, now also if I define a point B, so I'll put it somewhere over here, and then I can draw a vector going from O to B, so the arrow points from O to B, and I've now got my vector OB defined. Now in this instance I need the vector AB, so it's got to start at the point A in the direction of B. So I have to figure out what this vector AB actually is. Well, to do that, I'm starting at the point A. That's where I've got to begin. And I've got to get to B. Now I can do that by going back to the origin via OA and then going from the origin to the point B via OB. So you'll remember this from previous years. If I want to find the vector AB, I simply have to travel in the direction AO and then in the direction OB. And you can see that the letters I require, the A and the B, are on the flanks. They're on the outside. And then also the letters on the inside correspond, which means I'm taking a journey from point to point. So you know you've done it right if that's the case. Now, continuing on from that, if I go in the direction AO, that's the opposite way of the vector OA. I'm going against it. So I'm going from A here to O. So I'm working against the vector OA. So I'm actually going in that direction. So to do that, I can just change the sign of my vector OA. So it's going to be like this. So it's going to be negative OA. It's the same thing. Plus OB. All right. Now, if I do that, let's just plug the numbers in now. So this is going to be minus, and we'll put the vector OA in. So it's going to be I plus 5j minus 2k. You can use column vector notation for this as well if you want. Plus OB, so that's going to be subtract 3j plus 7k. All right. Now, if I just change the signs of all this, so this is going to be negative I, subtract 5j, plus 2k, subtract 3j, plus 7k. Just collect your i's, j's, and k's together now. So we'll do the i's first. So I've got negative I here, and there's no other i's on the screen. So this is going to equal negative I. For the j's, we have negative 5 lots of j here, subtract 3 lots of j there, so that's negative 8j. And for the k's, I've got 2 plus 7, which is, of course, 9. So that's plus 2k plus 7k, which is plus 9k. All right, now it's asked for this in as a column vector. You could have done this as column vectors all the way down, but as a column vector, it's going to be negative 1, negative 8, and 9. Okay, so I hope that makes sense. Okay, example 2, we've got two vectors A and B given in column vector form, and we have to find two combinations of A and B, linear combinations, in fact. So for part A and part I, we have to find out what 4A plus B is. So I'll just write it down first of all, and we just sub in the vectors. We can do this in column vector notation all the way through. So this is going to be 4 lots of the vector 2, -3, 5, as it's defined in the question, plus 4, -2, 0. Now, you'll remember from year 1, if you're multiplying a vector by a scalar, which is what we have here. So this is what we call a scalar. You simply just multiply all the components by that scalar. Okay, so just make a note of that. So this is what we call a scalar. It's a coefficient, essentially, of your vector. So we just have to take the 4 right here and just multiply it by all the different values inside that column vector. So it's simply going to be 2 times 4, which is 8, 4 times 3, which is -12, and 4 times 5, which is 20. Okay, and then we add b onto that. So plus the 4, the -2, and the 0. And if we combine all that together, we get 12 for the I components, -14 for the J's, and 20 for the K's. Okay, so that's AI. Now for part 2, it's exactly the same process. So we need 2a subtract 3b now. So 2a subtract 3b. Well, we plug in the numbers again. This is 2 lots of a. That's 2, -3, and 5. Subtract 3 lots of b. So 4, -2, and 0. So this time we've got to multiply both a and b by scalars in this instance. So firstly, let's look at the 2 multiplied by the a. Okay, and we'll just write what we get there. So we've got 2 multiplied by 2, which is 4, -6, and 10. Okay, so that's done that one. And then we're going to subtract. I'll leave the subtraction here. And then we're going to multiply everything by 3. You could also add and multiply the vector by -3 if you want to, but I'm going to leave the negative there and just multiply by 3 inside the vector. You can do either, it doesn't matter. All right, so 3 multiplied by everything, that's going to be 12. 3 multiplied by -2 is -6. And 3 multiplied by 0 is 0. And just combining all of that, 4 subtracts 12, which will give us -8. -6 plus 6, which is 0. Okay, and then 10 subtract 0, which is, of course, just going to be 10. All right, so that was fairly straightforward, I think. Now for part B, we're asked something a bit deeper. State with a reason whether each of these vectors is parallel to 4i subtract 5k. Now that's quite interesting. Now 4i subtract 5k, I'm just going to rewrite that in a slightly different way. As a column vector, I've got a bit more space up here. This would of course be 4 lots of I. Now there's no j's at all, but there is -5 lots of k. Now looking at that, we know that if vectors are parallel, then one of the vectors that we have here, the 4a plus b, which I have over here for part AI, and the -8, 0, 10, which is 2a subtract 3b for part A double I, those vectors have to be scalar multiples of this vector here if they are parallel. Now we can straight away disregard the first one. Okay, this vector here can never be a scalar multiple of 4i subtract 5k. And the reason is, of course, because the j component is non-zero. Okay, what the j component has to be, this j component here, that j component has to be a multiple of 0. So it has to be 0 in order for it to work. So the only potential parallel vector would be AI part 2, which is this one. Okay, simply because we have this 0 over here in the j component. So let's see if it is indeed a scalar multiple. So for part B, we can disregard A part I for the reasons I've just suggested. Now, let's just test AI part 2. If we do that, then the vector we've got, the -8, the 0, and the 10, must equal some scalar multiple, I'll call it lambda, of 4, 0, and 5, -5. Now, I don't know if that's true. I'm going to put a question mark there. So we have to check. Now, if you look component by component, we've got 3 equations to solve for lambda. We've got -8 is equal to 4 lambda, first of all. Now, if we solve that equation, looking at the I components, four lambda would equal -8. Now that would imply that lambda would equal -2, right? But this has to be true for all the components. It's got to be the same scalar multiplying each one. If the scalar is going to be different, then it's not going to work. So we have to check that we get lambda equals -2 for the j's and the k's. So let's have a look at the j's now. Now the j's is a foregone conclusion because everything is 0. So we just get 0 equals 0. So that checks out. It doesn't really tell us anything. Or even you could just say lambda times 0 is equal to 0, but that's by the by. Now, the one we really need to check is the k component, okay, for each one. So k's. So we've got -5 lambda is equal to 10. So that implies that if I divide by -5, I get lambda is equal to -2. So again, we've just shown that it is indeed parallel. Okay, we've got the value of lambda is equal to -2. So just to answer part B in conclusion, so state with a reason. So we can see that the vector 2a subtract 3b, which we found earlier, is equal to -2 multiplied by the 4i subtract 5k. We have just shown that is the case. So that, because it's a scalar multiple, hence they are parallel. And the reason is the mathematical argument that I've just given. Okay. So that's worked example 2 concluded. So in worked example 3, we need to find the magnitude of this vector given here. And once we've got the magnitude, as we saw in the warm-up, we can then find the unit vector, okay, a hat, as we call it. So first thing, let's find the magnitude of a, and then we can write down what a hat is. So for the magnitude, remember this is the absolute value. If you like, that's the notation we use. And we just plug in the 3 components into Pythagoras' theorem. So that's going to be 2 squared plus -1 all squared plus 4 squared, square root the whole thing. So this is going to be the square root of, now just do this bit by bit, so that's going to be 4 plus 1 plus 16, which gives us the square root of 21. Okay, now that's the magnitude of the vector. So we have to state that that's in some unit. We don't know what it is, but we just acknowledge that anyway because it's a distance. And hence, so we use what we've just done to find the unit vector. So a hat. Now remember from earlier, to define a unit vector, we take the vector A and we divide it by its own magnitude, which scales down the vector A, which is pointing in the correct direction, but it scales it down so that the magnitude is just 1. Okay, so we can just write this down. So the vector A, which is 2i, subtracts j, 4k added on. We divide the whole thing by what we've just discovered, which is the square root of 21. And once again, there's nothing wrong with that answer, but just for convention and from what we've learned on surds, we're bringing that surds knowledge back in. We can rationalize all this. So I'm going to multiply the numerator and the denominator by root 21 just to rationalize this. Okay. And we can do it component by component as well. So we're going to have, first of all, 2 root 21 over 21, and that's the I component, subtract root 21 over 21, lots of j, plus 4 root 21 over 21, lots of k. And this is what our a hat is equal to. As an exercise, just to verify this, if you have time, if it's an exam or whatever, just verify if you apply Pythagoras' theorem to all this, as complicated as it looks, okay, Pythagoras' theorem to all that, you should find that the magnitude is 1 as was requested. So we're now going to introduce some trigonometry into our work on vectors, and we can find numerous angles. We can find angles that that the vectors in 3 dimensions makes with either a coordinate plane or with coordinate axes themselves, and that's what we're going to look at now. We're going to look at the latter. So I'm going to define a vector. I'm going to call it the vector A in this space, so you can write this down in the space provided. So the vector A is just going to be an arbitrary point. It's going to be x in the I direction plus y in the j direction plus z in the k direction. All right, so this is a position vector. Okay, so therefore, let's define the position vector. So OA is just going to be x, y, z. I'm writing it in column vector form just to get us used to everything. And if you want to, just for completeness, the point A on our coordinate grid is just going to be at the point x, y, and z. So we've got all bases covered there. All right, so let's put this on our coordinate grid. Now I'm going to build it up piece by piece, just so that we are clear about how this works. So we go in the x direction first. I know from all these points there that the the I component is going to be x. So I'm going to assume it's a positive value. So I'm going to go from the origin, which is not labeled on the diagram. So I'm just going to label that. So the origin is here, and I'm going to go x units along. So I'm just going to assume this is a positive value. It doesn't matter. So I'm going to stop when I get to x. Okay, so about here. Okay, so that's my x component. Now I'm going to travel in the y direction. So if you notice, we've got y positive y in the j direction, and here as well. So I need to travel in the y direction now, so which is perpendicular to the x direction. So it's going to be something like this. So about there. So I've now traveled in the y direction. So it'll be somewhere here, I think. So on my coordinate plane, my 2D coordinate plane, this is going to be the point just x, y, as we saw earlier when we were defining the distance in 3 dimensions. Okay. Now we've just got a single point there. Now what I want to do is add the 3rd dimension. So we're going to go in the z direction now. So looking at, we're going to go z in the k direction there, as acknowledged in the other 2 formats. So I'm going to go upwards in the z direction. So let's see what this looks like. So I'm on the surface of the table, if you like. So I'm as far as z goes, I'm still at the origin. So in the z direction, I'm going to go up some amount. So let's say to about there. All right, so z about here. Now I've got to do the same thing where my xy coordinate is. So I'll try and mimic that. So it's going to go up in the z direction to about there. Something like that. Perhaps would be a bit higher, maybe. It's hard to judge, isn't it? So I've now defined a point in 3D space. Okay, and you've got to use your imagination a bit for that, haven't you, really? Okay, so this is now the point x, y, z. Considering all 3 dimensions. So I can now draw my position vector. Now my position vector is called A, as we defined it right here. So I need to draw a vector that's going to go from the origin to the point A. So let's do that. So starting at the origin, and this is traveling in 3 dimensions. That's my vector A. Nice pink color. Okay. And we'll label this point A, which I haven't done yet. So that's going to be the point A, and everything seems to fit together. All right. So I hope that makes some sort of sense. Now, what we're interested in is finding an angle between the vector A and one of the coordinate axes. Now, I'm going to choose the x-axis for this because the diagram is set up for me to do so in a quite a simple way. So if we look at the x-axis as the axis that I'm interested in, the vector is obviously in 3 dimensions, but it does actually make an angle with the x-axis, and the angle looks like this. So if I draw an angle from the vector to the x-axis, it's an angle at an angle, if you like. So imagine that I complete a right angle triangle. So I'm just going to do that, and hopefully you can see it. So if I draw from my x coordinate a straight line to my point A, I've now created a triangle that is 2-dimensional, but it's sat in 3-dimensional space. So it's not really 2-dimensional, but it's in a 2-dimensional plane. So it's creating a 90-degree angle like that, and it also creates this angle between the vector A and the x-axis. Okay, so I can now talk about that angle. I'm going to call that angle theta x, x with as a little subscript. Okay, so it's a tilted angle. How do we find theta x? Well, we can use simple right angle triangle trigonometry. So if we look at the sides that we know, well, I'm going to assume that I know this x value here. And to get the hypotenuse, I can just simply take the absolute value of this vector A. So hopefully it's clear that if I want to find the cosine of theta x, it's going to be the adjacent over the hypotenuse And remember, these have got to be distances. So x is a scalar. Okay, it's not a vector quantity. It's going to be x over the magnitude of my vector A. Okay, now I've chosen cosine here because you'll notice that there's a nice correspondence between having the x in the numerator and the x here. Now I could have used sine, but we would have had to have done a little bit more work, because if I use sine, I would need to find this length here, but this is also the hypotenuse of this right angle triangle here. So it just makes it more complicated. The x value is as it is, and we can lift it directly from the diagram. Now, similarly, if you want to find the angle made between your vector in 3 dimensions and another coordinate axis, the correspondence is exactly the same. So if I wanted to find the cosine of the angle made with respect to the y-axis, that would simply be y over the absolute value of your vector. And I can leave that for you to deduce if you want to as an exercise. You would just need to redraw the diagram and just relabel the axes essentially. And also, if I wanted to find the cosine of the angle with respect to the z-axis, it would be the z coordinate over the absolute value, sorry, I should say the magnitude of your vector A. And you can see the correspondence really clearly. Okay, so we can bring in a bit of trigonometry here to find some angles. So for example 4, I've just written out the 3 variants of the formula for the cosine of the angle made between the vector A and each of the coordinate axes. So once again, you can see the correspondence here between the numerator, which is the adjacent side, and the angle that you're finding. So the common ingredient for all 3 of these is, of course, the absolute value of A, which features in the denominator of each of these. So we'll figure that out first, and then we can talk about what the angles might be. So you might need to use a calculator for this question to get the angles. Now, it doesn't specify what units to write the angles, so whatever's convenient for you. I'm going to use degrees for this. We'll get onto that in a moment. So first of all, let's find the absolute value of, I shouldn't say that, the magnitude of A. It's not doing modulus function. So the magnitude of A, so Pythagoras' theorem on the 3 components. So that's going to be 2 squared plus -3 squared plus -1 squared. And just so you're aware, in case you haven't cottoned on already, these are the where the numbers are taken from. -3 right here, and lastly the -1, which is the -1k right there. All right, so you should be familiar with that now. So we just evaluate this. So this is going to be the square root of, so we've got 4 plus 9 plus 1, which is simply going to be root 14. Okay, and we won't need to rationalize any of this. We're just going to plug the root 14 in. All right, now I'm just going to partition this. It's not quite partitioned as I would like this particular bit. So if we're going to look at the cosine of the angle made with the x-axis, this is going to be the x component, which is 2 divided by root 14. Okay, now then, because that's positive, I mean, we could worry about things like cast and stuff like that, but because this is a positive value, we can just return an acute angle on our calculator. Now I'm going to do that, but I just want to bring in cast just for a second, because if we draw a cast diagram, now the horizontal part of the cast diagram would be your x-axis. Okay, and you would label everything as normal, CAST, And because the value is positive, this is a positive value right here, okay, we'd be interested in the C and the A. Your calculator, however, will only return an acute angle when you plug a positive number in. So it's this angle here that we're going to get. So this would be your theta x, which is exactly what we want because it's the angle made with the x-axis. All right, so it would do the job for us. So let's figure that out. I've just set my calculator to degrees. Now let's plug all this in. So we need to use the shift cosine button and we plug in the numbers. That's going to be 2 over the square root of 14. Just come out of that, close our bracket, and see what we get. Okay, so we get 57.7. I believe we want the answer to 1 decimal place. Just wanted to remind myself. Yes, we do. Okay, so that's our theta x. So therefore, theta x is going to equal 57.7 degrees. Okay, so that's the first one. Now, we repeat this for theta y and theta z. So let's bring this down. Let's partition that off. So if we do cosine of theta y, now you'll notice this is a negative value. So this is going to be negative 3 over root 14. Okay, now on a CAST diagram, again, I'm going to draw this again. This is an important idea. The horizontal line would correspond to the y-axis in this situation. And again, you can just add the letters, so C, A, S, and T. And what you can do, I mean, it's up to you how you do it. You can actually just plug in the negative value straight into your calculator, and I'll explain why. If you plug in a negative value, if cosine is negative, then it's these two quadrants that will be flagged up. And your calculator, if we just do it, I'll show you what I mean. So if I just bring the calculator back up, just close that, and we're going to do the inverse cosine of negative 3 over the square root of 14. And again, I'm just going to come out of that. And we get 143.3. Now, that's quite interesting. So it's an obtuse angle. So what this means is that, I'm just going to put it on the diagram. I'll stick to the color scheme. If you plug in the negative value, the calculator deals with that for you. It tells you that this is your theta y, which is 143.3 degrees. It's an obtuse angle. Now, whether you put your negative value, if you ignored the negative value, of course, here, and you put it in these quadrants, you would get the acute value, but that would be this angle here. And it would also be the same angle in this quadrant. But you'll notice, of course, that it's the same obtuse angle measured in that direction. So that would also be theta y. It doesn't matter. It's the same value. And it works because you're measuring the angle okay, as it says in the question, makes with each of the positive coordinate axes. Okay, and that's a typo. I've just noticed that should be positive coordinate axes. So it doesn't matter which direction you do it, you still getting the same theta y. It's still the same obtuse angle. So the formula works absolutely perfectly, and you don't really need to worry about CAST or anything like that. You can just plug the numbers in as they are, because you're either going to get an acute angle or an obtuse angle, and you can only get an acute or obtuse angle with the positive coordinate axes. So we'll just jot down the answer. So theta y, which was 143.3, 143.3 degrees, like that. Okay, and then finally, and I won't draw a diagram for this one, cosine of theta z is of course just going to be -1 over root 14. So what I'm going to do now, I'm just going to edit what was on the calculator a moment ago. So go back into that, just change the numerator to -1, and let's see what we get. 105.5. Okay. So therefore, theta z is 105, done that again, 0.5 degrees. Okay, and all of these are to 1 decimal place. All right, so I hope that makes some sort of sense. The CAST diagram kind of figures, but because you're only dealing with acute and obtuse angles, by plugging in the negative values, it will just return the obtuse angle, which is exactly what you want anyway. Okay, so let's move on to example 5. For our final example, we're going to show that hopefully triangle OAB is isosceles. So this is just the 3-dimensional version of what we looked at already in the warm-up. So if you haven't tried this already, you can pause the video, try it, and then obviously come back and we'll see if we can get the same conclusions. Right, so the points A and B, we have position vectors. Now, for the position vectors, it depends how you want to write them. So OA, you can write that as 4i plus 2j plus 7k. If you prefer, you can write them as a column vector. It's completely up to you. That would be 4, 2, and 7. Okay, but both equally valid. And then for position vector of B, OB, that is 3i plus 4j subtract k. And again, you can write that as a column vector. So that would be 3, 4, -1. The other consequence of this, of course, is that the coordinates of A would be 4, 2, and 7. And the coordinates of B would be 3, 4, and -1. So just different ways of expressing the same kinds of things. All right, now we have to find the vector AB and show that triangle OAB is isosceles. So as we did in the warm-up, let's just sketch a triangle. So we've got a point of reference. It doesn't really matter what the triangle looks like, okay, as long as it's labeled. So O, A, and B. So I'm just going to draw some sort of scaling triangle. For now, we can't be absolutely definite that it's isosceles. So I'm going to call that bit the origin O. I'm going to call this point here A and this point B. All right, and then the vectors OA and OB. Okay, so first port of call, let's find AB. Well, the vector AB, quite straightforward. I start at the point A, I have to go back to the origin, and then I have to add the vector OB, moving in that direction. That's all you have to do. So this is going to be AO plus OB, and also just to verify, just check that these letters correspond. The letters on the outside must correspond, as you can see, because I'm going from A to B, and then the letters on the inside must match to show that we're going point to point. Right, so let's apply the ideas of vectors. So AO is going the reverse direction. So I'm going from A to O in that direction. It's the reverse. So it's the same as negative OA plus OB. And if I do that, I can just multiply my OA vector by -1 essentially. So I'm going to use the column vector notation for this. So it's -4, 2, 7 plus the OB, which is 3, 4, -1. All right. Now I think we can do this in one go. So essentially, this is going to be -4 plus 3. Hope that makes sense. So -4 plus 3, which is of course -1. Then I've got -2 plus 4, which is 2. And then -7 subtract 1, which is -8. All right. Okay. If you want to put an extra step in there, feel free to do that. So that's my vector AB done. Okay. And AB, of course, goes from A to B. Now then, we have to show that triangle OAB is isosceles. Now, to do that, we're going to need the magnitudes of each of these sides. So for the next bit, we're going to need to find the magnitude of OA, the magnitude of OB, and the magnitude of AB. And once we've done that, we should have two the same. Remember, isosceles means that we've got two sides of equal length. Only two. Remember, if it's all three, that's equilateral. If it's none, then it's scalene. Okay, so let's figure out, and then we can use Pythagoras. So the magnitude of OA is simply going to be the square root, and we just plug in those numbers. So plug in these numbers into Pythagoras' theorem. So it's going to be 4 squared plus 2 squared plus 7 squared. Okay, which is equal to the square root of 16 plus 4 plus 49. Which is root 69. Okay. Now then, do the same thing for OB. Square it now. Plug in the numbers for OB, which is right here. Oops. So put these numbers in. So that's going to be 3 squared plus 4 squared plus -1 squared. I'm just going to extend my square root. Okay, so this is going to be the square root of 9 plus 16, okay, plus 1, which is equal to the square root. Now, so that's going to be 26. Right, so we've just established that OA and OB are not the same. So if that's the case, then the vector AB must be either root 69 or root 26. Otherwise, this is not true. So, but we're hoping it will be. Right, so the vector AB. So let's hope we've done everything correctly. So we need the magnitude of that. Now, AB is right here. We deduced it earlier. So we're going to plug those numbers in. Again, I'm going to use a different color here. So that's going to be -1 squared plus 2 squared plus -8 squared. All right, let's do this. So that's going to be 1 plus 4 plus 64. And I never draw my square roots long enough. I can never quite judge how long to do them. So this is root 69. Okay. Right. So there we have it. So we've now shown that we've done all the mathematics now. We've now shown that the length of OA is equal to the length of AB. So therefore, triangle, do it the right way around, OAB is isosceles. All right, you have to do all three. If you did OA and AB, and then concluded just from those two that this was isosceles, just from these two values here, that wouldn't be enough. You've got to show that 2 out of the 3 are the same, because it could still be an equilateral triangle. You've got to show that it's isosceles, as it states here. Okay, so there's lots and lots of skills on show there. Please try the exercise before we move on to the next lesson. Okay, thank you.